In the previous video, we introduced Markov chain Monte Carlo methods more broadly, and the Metropolis-Hastings algorithm in particular. And what we said was that this was a way that I could draw samples from some proposal distribution, and by accepting some of those and throwing some of those away selectively and with appropriate probabilities, I was able to turn a set of samples from the wrong distribution, so to speak, into realizations from the right distribution. And in this video, we'll just expand on that and explain a little more and go through some visual explanations of that. Exactly how MCMC operates is really going to depend on what we choose for our proposal distribution. Obviously, if I choose a proposal distribution that looks absolutely nothing like the target distribution, then, well, it'll still be correct, potentially, but it's going to waste a lot of time, because if it's proposing a lot of moves, that when the target distribution is compared to the proposal distribution, it'll just waste a lot of time throwing away these poor suggestions. And that might lead to the chain running extremely slowly or having issues with convergence. Now, I said this very briefly in the previous video. The original Metropolis algorithm actually suggested that we needed an entirely symmetrical proposal distribution, i.e. g of xp given x and g of x given xp. So proposing going from x to xp was just as probable as going xp to x. And in that case, it simplified the acceptance probability calculation. Now, there is obviously one, I suppose, very extreme case, but a little bit useless, which is when my proposal distribution is not just an approximation to the target distribution, but it is the target distribution. If I've already got the right answer, then you can easily see that the acceptance probabilities will all be 1, because there's no reason to edit the draws from the proposal distribution to get draws from the target distribution if my proposal distribution is my target distribution. Now, if you'll please excuse me referring to the distribution that we're aiming for as pi of x, was previously I've used p of x, one and the same. The aim of the MCMC method is to construct a Markov chain such that the equilibrium distribution of this Markov chain is my target distribution, which I'm now calling pi of x. So I start by setting up a chain which is reversible and making it such that the probability of moving from x to xp is equal to the probability of moving xp to x. Then what I've got is I have this fact that pi of x and xp, if either one after each other is equally probable, then I've got the pi of x times pi of xp given x has to be equal to pi of xp times pi of x given xp. That's just basic conditional probability. So if I now say, well, I'm not actually able to calculate pi of xp given x, but I can say what's g of xp given x. So I can say, what's the chance that the proposal distribution says go from x to xp? And then multiply by the chance that I actually do that, because then the probability that I actually go from x to xp is that the proposal distribution says, I think you should go from x to xp, and then the probability that I, actually do that. So I need to find an acceptance probability that satisfies that criterion. So if I just substitute all of this in to that statement and a little bit of rearrangement, then what you can start to see is the beginnings of how Metropolis, and then subsequently Hastings as well, and colleagues, derived that calculation of the acceptance probability. If I rearrange it this way, then we can really start to see this. Because obviously, the acceptance probability of xp given x divided by the acceptance probability of x given xp, well, one is going to be larger than 1 or greater than or equal to 1, and the other is going to be less than or equal to 1. If I just cap it at 1 by saying that if I set it to be the minimum of 1 and this ratio, then I have an acceptance probability that will satisfy the criterion that I ended the previous slide with. I like this visualization here. And it basically says, if I had to draw samples from this blue distribution, which I think we can all agree looks difficult, it's got a lot of local modes, got a lot of local peaks, they're skewed each, it's awkward, it sort of tapers away down towards 0 height. Whereas this red one, give or take my wonky drawing, is basically a normal distribution. Now, one thing I would note is these things are clearly not drawn on the same scale, because quite clearly the area of the red distribution is larger than the area of the blue distribution. That actually doesn't really matter. I can just think of these things as sort of on their own scales. But what I want to do is I want to think of, if I were given a load of samples from the red distribution, this sort of normal shape, how would I go around throwing bits of it away until what I was left with was the blue shape? And you can think of this a bit like a sculptor. If you were given a block of stone, the block of stone has to completely encase what you want to end with, and the sculptor's job is to strategically chip away at the bits that aren't needed until the shape that's left is the target, what you're aiming for. So if I do this by sort of comparing the relative chances in the blue distribution with the red distribution, but if I were drawing points here, I would say the red distribution here is a really good approximation of the blue, so I will always accept that. There is no space in the frequency with which the red distribution is throwing points up that aren't also in the blue distribution. Down here, of course, there's none of the blue distribution, but there is some of the red. So the red is throwing up points which are outside the blue, so those will always be rejected. But there's a lot of intermediate cases. So if I draw a point here from the red distribution, as I've drawn that, I'm claiming that the red height is twice the height of the blue height, so half of the red observations there would want to be accepted, and the other half would be chiseled away as an overestimate. Down here, I can see that there's a little bit of red that isn't overlapping with the blue. Say 80% of the red overlaps with the blue, 20% doesn't, so I'd have an 80% chance of acceptance, and so on. So you can think of it that way. How much of the red area, in this case, is also in the blue? I have to make sure that my proposal distribution can propose all the values that I need for my target distribution. If there's any area of the blue that would stick above the red, that would be the blue needs values here, potentially, and the red can't propose them, so that would be a problem. Doesn't matter if the red proposes far too many values in a region or proposes some impossible values. The Metropolis-Hastings algorithm will ensure that those are thrown away, but they will be a waste of time and resources.